In lesson 5.2, we're going to look at, again, more rational exponents, so more fractions in the exponents, and combining and multiplying and rewriting them. So let's look at some properties here. We're going to use our properties of exponents. Recall that when we multiply like bases, we're going to add the exponents. So I have a base of 81. That 81 is going to stay the same, but I want to take 5/6 plus a negative 1/3. I can't add fractions without a common denominator. So if I multiply my denominator by 2 here to get this to be 6, I'd multiply my numerator to become 2. So this will make it 5/6 take away 2/6. That leaves me with 81, and 5 minus 2 is 3. 81 to the 3/6 power. Now, I could do the power of 3 and the root of 6, but I can actually reduce that fraction right now and make this a little easier. Oh, by the way, this is 81. This would be 81 to the 1/2, because 3 out of 6 is 1/2, which is the same thing as the square root of 81, and we finally know that number to be 9. So we took something that had a base of 81 and these fractional exponents with negatives and the rules of multiplying and came up with our answer of 9. Now, when we have division, remember we can subtract. So I'm going to actually apply my first rule with power to a power. Whenever you have this is an x to the 1, a power of 1 to a power of 2/3 leaves me with x to the 2/3. And y to the 3rd to the 2/3 would be y to the 6/3. Which will reduce to 2. Now that power out here applies to all of this. So the denominator is going to be x 1/2 times 2/3 makes 2/6. Now we need to do a little reducing with these x's here. So I have 2/3 and 2/6. I'm going to reduce this one down here. This will be x to the 2/3, y to the 6/3, which 6 divided by 3 makes 2. I'll reduce that one right there. I'm going to actually write this. 2/6 is the same as 1/3, which makes it great when I'm trying to reduce. And now I'm using my division rule. Basically, every rule of exponents is being used here to reduce our x's. When I'm dividing like bases, I want to subtract their exponents. So 2/3 take away 1/3 would be 1/3. And my final answer is there. I'll look at one more try it here with you on part A. You might want to see if there's an easier root to take first. Again, you don't have to do the power part first. So 3 would be to the 1/2. That top one isn't going to change. That'll be square root of 3 up top. But in the denominator, I've got x to the 2/5. Now I got a little bit ahead of myself because I took 3 to the 1/2 right away. I'm going to just look at this 32 to the 2/5. I'm going to look at that as the 5th root of 32 squared. I want to deal with just the 5th root of 32. That means something times itself 5 times will be 32. Well, that's 2. So I would have 2 squared down there, but now I still need to take it to the 1/2 power. So I will have 3 to the 1/2 power is root 3 over 2 to the 1/2, 2 squared to the 1/2. These 2 to the 1/2 right here, you will multiply, because we multiply the powers when you take a power to another power. So 2 times 1/2 makes 1, and there'd be my final answer, the root 3 over 2. You can try part B and check it in your answer key. Now I've broken these up before in previous videos, but if you want the nth root of a product, here we have A times B, you can do them each separately. That sometimes helps you reduce them a little easier. For example, 16x to the 5th, I want the 3rd root. Well, the 3rd root of x to the 5th, we kind of wish these matched because a 3rd power and a 3rd root would be great. I do have 5 of them in here, but if I put 3 of them together, that'd be x to the 3rd, and the 3rd root of x to the 3rd would just give me x. But I have 2 more left over, so I would have the 3rd root of x squared left. This one, 16, is 2 times 2 is 4 times 2 is 8, and times 2 is 16. These 3 together could be called 2 to the 3rd, and if you take the 3rd root of it, the 3rd power and the 3rd root will cancel, but remember you still have this extra 2 out there. So we would have 2, which comes out because of the 3rd root of 2 cubed, that's this 2, And this guy is still stuck under that third root. We'd have the third root of 2 there. So we could rewrite this as 2x to the third times the third root of 2x squared. You basically try to reduce that radical and break out as many third powers as you can. So when we reduce a radical, you take all the nth roots, in this case the third roots, of perfect nth power. So these are a perfect x to the third and a perfect 2 to the third. Once you have those all out, we call it perfectly reduced. So for example, on try it part A, the fourth root of 81, hopefully by now maybe you're thinking that's a 3, because remember 3 times 3 is 9, and 3 times 3 is 9, and that'd be 81 if you multiply them together. Here though, think about this one. We could rewrite this as a to the 8 over 4, because the power goes over the root. That would be a squared. And this one, if I write this as b to the 5 over 4, I'm going to have 4 of them in here. I'd have b to the 4th times b to the 1. This b to the 4th can reduce with this 4th root and have a b come out there, but I still have one b left inside that 4th root. This right here would be our final answer. Almost everything reduced out of the radical except for that last b in b to the 5th. You may want to take a second to pause and put these in your packet, but the property of radicals when you multiply or when you take the quotient are here. You can break them up to help it make a little bit easier for you. Now when I look at this next one, I think it's a little bit interesting. We see they're both to the 5th root. There is no number that multiplies times itself 5 times to get 16 or 8. But remember, we can rewrite it as the 5th root of 16 times 8, and 16 times 8 is 128. Now we did do a reducing of radicals long ago, but 128 is actually 32 times 4. Well, the 5th root of 32 is doable because if we took 2, 4, 8, 16, 32, this gives us 2. We can take the 5th root of 32. The 4 will be left over in there. So our final answer will be 2 from the 5th root of 32, but that 4 is left in there. The 5th root of 4 stays. For part B, they have them as radicals, and I've rewritten them as exponents with fractions because the power is 1. Notice I use parentheses around the 2x and the 8x. The power is 1, but the root is either the 6th or the 3rd. When we are multiplying like bases, we could add them, but we don't have like bases. So in order to get these index numbers to be the same, I'm going to change this here. I'm going to make this a 6 by multiplying by 2. And so if I multiply the denominator by 2, I have to multiply the numerator by 2. Now I would have the 6th root of my 8x, which was first, times 2x is going to be squared now. So I'd have 4x squared. And that again is because it was a power of 1 with a 2x, but I had to change this to a 2 so it would get the denominator to become a 6. I had to double it. So all of this now has a power of 2. So I've squared the 2 and I've squared the x. Now we can rewrite this as the 6th root of 32x to the 3rd. And there's no way we can take anything out because there's no number that multiplies by itself 6 times to give us 32. And x to the 3rd isn't even high enough to have 6 x's in there. So we are actually just done reducing it and rewriting both of those terms under the same radical, the same root, if you will. Now again, this is a lot. These are a lot of rules, and practice is the best way you're going to get good at these. But if we look at this one, we have a third root of 2n over 9m. We know by our quotient property that we can write them separately, so that's what I've done here. But we do not leave radicals in the denominator. It's a no-no. It's almost as bad as dividing by 0. I want a perfect cube something in here so I can take a cube root and it will come out nice. I'm going to multiply by 3 the cubed root of 3m squared. And if I do something to the denominator, I have to do it to the numerator. Let's see why I would do that. Because they're both under the third root, the index is the same. I can still leave that third root and take 3 times 2 to make 6 n m squared. But in the denominator, I'm given 27m to the 3rd. This is great because I have 3 of these m's, the power and the root, I know the 3 times 3 times 3 makes 27. So my third root of 27 is 3. M to the 3 over 3 is just m, and my numerator stays as is. These cannot reduce anymore. So to get your denominator to not have a radical, you want to try to find perfect cubes or perfect n roots in this case to make it become just a number without a radical. I'll do one part of the try it here. I've rewritten this fifth root of this quotient separately. The top I'm not going to worry about, but I don't want that radical in the denominator. Now I know 2 to the 5th is 32. If I could get this number 16 to be 32, that would be great. So I'm going to take 16 times 2 to get it to be 32. And I want this to be x to the 5th, so it'll have x to the 5 over 5. That would reduce nicely. So to get x to the 5th, I can have x to the 3rd, but I need x squared then also, so I'll put x squared. Whatever you multiply the denominator by, you need to multiply the numerator by. So I would have the 5th root of 14x squared all over the 5th root of 32, because that's 16 times 2, and x to the 3 and x to the squared makes x to the 5th. I actually have now a 5th root of 32. We know that is 2. And the 5th root of x to the 5th is x, and we leave our numerator the same. For example 4, we've combined like terms before, but now we're combining like radicals. But they must have the same index, so the same root, like this third root and third root, and they must have the same radicand. Now that's a problem here because I've got 250 and 16. Those don't match. And both of those have to match in order for me to be able to add those two blue bubbles. So here I've rewritten square root of 20 as 4 times 5. Hey, we know the square root of 4 is 2. So that first term could be rewritten as 2 square roots of 5, because the square root of 4 is 2 and the 5 is left. Minus, I know that 8 times 2 is 16, but the third root of 8 is 2, because 2 times 2 times 2 makes 8, and I leave my third root of 2. 250 is 125 times 2, and I happen to know the third root of 125 is 5. Leave my third root of 2, and then I have minus root 5. By combining the like terms, I have 2 root 5s take away a root 5. I have 1 root 5, and negative 2 third roots of 2 plus 5 third roots of 2. Notice how these match now. I will have plus 3 third roots of 2. You want to combine those like terms, but you have to have the same radical index and radicand. This will become a big thing that you can reduce those radicals to get common radicands. So quickly here on a try it, notice that on part B, 20 is 4 times 5. Square root of 4 is 2. The 5 gets left in there. 100 times 6 is 600. The square root of 100 is 10. Leave root 6. And square root of 25 times 5 is 125. So the square root of 25 is 5, and leave the root 5. The ones I can combine are the ones that have the matching root. They all have the matching root, but only these 5s will go together. So I'd have 2 root 5s, take away 5 root 5s, is negative 3 root 5s, and then minus 10 root 6s. You can't combine the root 6 with the root 5 because their radicands don't match. We can multiply radicands as well. So let's take a look at this part A. Now I've multiplied 2 times the third root of 7, and the third root and the third root multiply by each other to give us the same root and 7 times 49, which makes 343. Notice how our index stays the same. But 343 is really 7 times 7 times 7. I know the third root of 343 is 7, and I have, this one can't be reduced at all, so I would just have 2 third roots of 7 minus 7 as my answer. Here I have my 4x squared. I've done my rainbow distribution here, multiplied them carefully. My middle terms actually can combine. I've got negative 4x root 3s, and the square root of 9, because 3 times 3 is 9, it's still the square root, would make 3, and that would be our final answer. You can try the try-its and check the answer key from your teacher. Finally, we don't want radicals in the denominator. So when you have a radical with a plus or minus sign, you need to multiply by what's called a conjugate. It's basically the opposite. So here I've multiplied by our conjugate, 2 minus root 5, and simplified.